Good evening, everyone. I'm Professor Andrei Zvelindovsky, Head of School of Mathematics and Physics at University of Lincoln. And you can see an image of our Isaac Newton building of University of Lincoln just behind me. Very pleased to see people from all over the world. We see AC from San Diego, for instance. Good day there. There are lots of people from nearby. Very, very pleased to see you all. We had a little bit of break in time between our Astro-Chats, but nonetheless, now we meet again. And I'm very happy to be joined by our distinguished speaker, Professor Don Kurtz, who is quite far away in South Africa. What weather is like there, Don?
Andrei, we are approaching the winter solstice. It is freezing winter here. I have no heating in my house. Today it was only 20. Tonight will probably drop to 12. Sunny, beautiful walk on the beach. Seal swam by in front of the house today. So it's tough.
Right. Okay. Yes. Tough winter in South Africa. This is our 18th Astro-Chat. And many of our visitors are regular ones, so there's no need to introduce Dawn again. And if you're new to our Astro-Chat, please do check the link in description to this video, where you can find a biography of Don. But you also can simply look on Wikipedia, because Don is famous and you can find him on Wikipedia as well. You can ask questions the same way as you type your hello and good evening now, in the same way in Astro-Chat, and we'll try to answer them after the presentation. And without further ado, I'll give floor to Don.
Thank you for the introduction, Andrei. Hello, everyone. I'm glad to be back. Sorry it's been so long since we last got together. And let me now switch over to my presentation, and we'll get started. So my question for tonight to discuss with you is, how far away is the sun? And you know the answer to that. Of course, your mom told you that when you were 4 years old. You learned that the sun was 150 million kilometers away. Or AC in San Diego, you probably learned that it was 93 million miles away. But it's a number that you know. And so what tonight's talk really is about is, how do we know? Because there's a picture I took of the sun at sunset from just above the bridge of the Queen Elizabeth cruise ship when we were sailing out of Sydney. I lecture on cruise ships too. And you look at the sun in the sky and just say, well, how far away is it? How can anybody know? For thousands of years, humans tried to find that out. And tonight, I'll take you through the pathway that led us to discovering the distance to the sun. And then I'll give you some mention at the end of why that really matters. Our story begins on the 24th of May, 1543, in a small town in northern Poland. It was called Frauenburg then, it's called Frombork now. And in a tower in the fortified walls of Frauenburg, 24th of May, 1543, a 70-year-old man lay on his bed in a delirium, dying from a brain hemorrhage. Into the room walked his assistant, who brought to him his published work of his life work and put it into his unfeeling hands. The man never regained consciousness to know that his life's work had finally been published, but it changed the history of science and the history of humans. There's the tower that he lived in. He lived in this top room here for over 30 years. He only ever made a few astronomical observations. Otherwise, he was a theorist and thought about what the universe should be like. His name was Mikołaj Kopernik in Polish. The Latinized version of that is Nicholas Copernicus. He was a physician and produced useful ideas and work as a physician. He was a canon in the church, and he was an astronomer. He was not a very colorful character. There aren't lots of anecdotes about his personal life, and in many ways, he was maybe the least colorful character in all of history who has had such impact on the direction of human thought. What Copernicus did was he brought back a 2,000-year-old idea that the sun was at the center of the solar system, and then they thought the universe, rather than the Earth. So Copernicus's book on the revolutions of the heavenly spheres brought back the heliocentric hypothesis that the sun is at the center of the solar system. And with that idea, Copernicus was able to use observations to determine the scale of the solar system. This diagram gives you some idea how he would determine the relative distance of Venus and Mercury to the sun compared to the Earth. So in this diagram, not to scale, of course, the sun's at the center, and there are the orbits of Mercury, Venus, and the Earth, drawn as circles, which is not quite correct, but good enough for this discussion. And from the Earth, when we look at Venus in the sky, now it's very close to the sun right now, but it will be coming back in the evening sky and moving away from the sun through the rest of this year. The farthest Venus can get from the sun in the sky is 47 degrees, and that's very easy to measure. You can just watch how far apart Venus is from the sun in the sky. And with a little bit of trigonometry, you can discover that Venus is 72% the distance the Earth is from the sun, where the distance the Earth is from the sun is called the astronomical unit, or AU. You can do likewise with Mercury, which doesn't get as far from the sun because its orbit's smaller, 23 degrees, and you can find that its relative orbit is only 38% of the distance the sun is, distance the Earth is from the sun. And so there's Copernicus's determination of the relative scale of the solar system. He found Mercury to be 0.38 of an AU, Venus 0.72, the Earth 1 by definition, and then Mars, Jupiter, and Saturn. Saturn being the hardest, it moves the slowest in the sky, it's farthest from the sun of the naked eye planets. Compare those to the modern numbers. He did very well. So from Copernicus's time, 1543, we knew the scale of the solar system. What we didn't know was the astronomical unit. We did not know how far away the sun was. And Greeks had made some attempt at estimating that. They terribly underestimated it, and the methods were exceedingly difficult and couldn't really do the job. Following Copernicus, 3 years after he died, Tycho Brahe, well, in Danish, Tycho Brahe, that was Latinized to Tycho Brahe, and then we often anglicized the Tycho to Tycho in English, and so I will call him Tycho. Tycho Brahe was born in 1546 in Denmark to a very wealthy aristocratic family. His father was Otto Brahe, who became the governor of Helsingborg Castle, which basically controls the entrance to the Sund that goes through to the into the great northern trading towns of Northern Europe, and the taxes rubbed off on the Brahes before they got to the king. The Brahes were very wealthy. Tycho's father and mother, who were, Birta was his mother, Otto was his father. They had an agreement with Otto's brother Jorn, who was a vice admiral in the Danish Navy, that when they had a second son, they would give it to Jorn and his wife Inga because they could have no children. And as it turned out, their first children were twins, twin boys, and Tycho was the second born. The firstborn died while he was being weaned, and so only Tycho was left, and the parents were not willing to give him up. The uncle was not happy with that. And after about 2 years, Uncle Jorn simply kidnapped Tycho and took him. The two brothers, Otto and Jorn, came to an agreement without breaking the family. And Tycho was raised by his Uncle Jorn, who was vice admiral in the Navy. He was extremely wealthy, well-treated, well-educated, and he was expected to grow up to be a governor of a castle, to ride horses and to do the things that aristocrats did. But when Tycho was only a teenager, there was an eclipse of the sun. Now, here's a modern map of that eclipse. The totality came out of Newfoundland and came across North Africa. Up in Denmark, it was only a partial eclipse, but Tycho was stunned that the astronomers could predict when the eclipse would be. And then he was unhappy because they got it wrong by a day, and he thought that that really could be done better. And so he set himself learning astronomy, had a desire to become an astronomer, and he wanted to make the observations better so that things like predicting eclipses could be done more precisely, and because he wanted to discover the nature of the solar system, the universe, and perhaps be the most famous scientist of all time. Tycho went to university in Germany, and at a wedding party later in his teens, he and another student who happened to be his third cousin got into an argument. That was at the professor's house. And the argument was about who was the best mathematician. And you know how to solve the question of who's the best mathematician. They decided the way to do that was in a duel. And several days later, they had a duel. They had a sword fight. Tycho lost the sword fight. He didn't lose his life, but he lost the center of his nose. He and his cousin later became good friends the rest of their lives. They got over the duel. But in this picture of Tycho here, much later in his life, it's hard to see, but if I blow it up, you'll see that the artist has actually put it in. You can see there's the prosthesis in the middle part of Tycho's nose, which was cut out. And he was very, very proud of this prosthesis. And for formal events, he would wear gold and silver noses, although recent research on it has indicated that most of the time he wore a brass nose. This artist has chosen to present it as a flesh-colored nose. In the Tycho's 20s, he saw a supernova, 1572, and he wrote a treatise on that. It was on the new star, and in this particular diagram, this is the new star, which hadn't been seen before, and that showed that the heavens weren't unchanging, which were the dogma at the time, that the heavens were perfect and unchanging. And he was able to show with measurement that that star was certainly farther away from the moon, and therefore the heavens were not unchanging. Tycho was very favored by King Frederick II. Frederick provided an extremely large income for Tycho. At one point, Tycho had the highest income in Denmark after the royal family. And he was given an island called Havane, which is just off the coast of Copenhagen. And if you ever fly into Copenhagen or out, as you fly one side or the other in and out of that airport, if you're on the right side of the plane as it turns, you can look down right onto the island of Havane, where Tycho built an observatory to observe the skies and pursued his astronomical observations. Here is a picture of Tycho late in his life, and this drawing shows an arch over his head, and the arch shows his family history, because he's an aristocrat. At the top are the Brahe family, his father's family, the Biller family, his mother's family, but down the sides are the names of his other family ancestors. And Tycho was famous throughout Europe in his lifetime. Well, around 1600, one Englishman, 18 years younger than Tycho, was writing a play about a Danish nobleman, Hamlet. And of course, Shakespeare needed Danish names. And it's quite clear he must have been aware of Tycho, because two of the ancestors here in Tycho's arch are Rosencrantz and Guildenstern. And so almost certainly this is where Shakespeare got Rosencrantz and Guildenstern for Hamlet, because of the fame of Tycho throughout Europe. His estate on Havane was a big castle with beautiful formal gardens. You can see the giant gatehouses off at the corners. And then elsewhere on the island, he had his observatory. Now, the telescope had not been invented at that point, so his observatory was made of pointing devices. There was a giant quadrant here with a long sighting device that he could sight along, other instruments. He could measure the positions of objects in the sky, particularly the stars, which he cataloged on a large brass sphere, and the planets which moved amongst them. He could measure them to a precision as high as 1 minute of arc, which is 1/30th the diameter of the moon. It was unprecedented high precision observations, and he carried out those observations for over 20 years. He wanted to use them to discover the nature of the solar system. Problem arose, though, because Tycho was a despot. He mistreated the families that lived on his island. He overtaxed them. He put some people in his dungeons. And when King Frederick, his patron, died, the new king, King Christian IV, who Tycho had known since he was a boy, he grew up to be king, and the people petitioned King Christian to have Tycho to ease off on his taxing and not to treat them so badly, and the king ordered him to do so, and Tycho ignored the king. And after ignoring 3 letters from the king decided to cut Tycho's stipend. And as is true today, as is probably true with most people you know, perhaps all of us too, if somebody cuts your salary dramatically, you're probably unhappy. And Tycho was not happy with the reduced income. And so he looked around and he managed to pick up a position as the imperial mathematician to the Holy Roman Emperor in Prague. And he immigrated to Prague, where the Holy Roman Emperor, Rudolf II, was a great collector. Now, he was a fantastic art collector. Some of his art collection, excuse me, was dispersed by attacks from the Swedes later, but a very large part of the art collection of Rudolf is now in the Art Museum in Vienna. And Rudolf also collected oddities. And one oddity he collected was Tycho, to come be his imperial mathematician, to be his astronomer, to be his astrologer and cast horoscopes. And Rudolf also liked the Italian artist Arcimboldo, and he had him paint a painting of Rudolf, which Rudolf liked very much. And so there is Arcimboldo's painting of Rudolf, where everything is a fruit or a vegetable or something else. And Rudolf was quite pleased by that. So Tycho was making his observations in Prague. Now, one evening, Tycho was at a dinner party with a baron who was speaking, and Tycho had been drinking a lot of beer. He really needed to get up and go relieve himself, but it would have been impolite to get up while his host was speaking. And he managed to hold himself until he burst his own bladder. And it took him about 5 days to die of that, but he did die in pain. And he died saying, "Let me not seem to have lived in vain," because he had not solved the problems that he wanted to be famous for. Well, before he died, in order to work on his project, he hired an assistant. And his assistant was Johannes Kepler. Johannes Kepler was a German mathematician, scientist, who came from a very different background. Johannes Kepler's father was a soldier of fortune who would go away to a war, come back again. He and Mrs. Kepler would have another child. He'd go off to war again. And after 8 children, he went off to another war and he simply didn't come home again. It's not known whether he had another family. If he was killed, he just disappeared from their lives and from history. And Johannes Kepler was sickly from a child. He was possibly a hypochondriac, or maybe he was really sickly, but he felt himself in ill health his entire life. But his mathematics and his reputation were so good that Tycho hired him and brought him to Prague to work on the data that Tycho had collected over more than 20 years of observing with his observatory in Fane in Denmark. But Tycho didn't want Kepler to be the one to make the great discovery. So what he did was he gave him the data for Mars, because Mars is difficult. Mars has a highly eccentric orbit. We'll come to that in a moment. But Tycho knew that Mars was difficult, and so he chose to let Kepler work on that so that he could make some advances, but let Tycho make the discoveries. Now, you have to remember that these calculations were not done with a calculator, with a computer, with any sort of aid. Everything had to be done by hand. And you shouldn't think of Kepler as having sat at his desk for decades making calculations. That's not how he worked. His piles were so bad he couldn't sit, and so he stood at his desk for years and decades making these long calculations. When Tycho died, Kepler inherited the observations, and this was 1601, so you can see 8 years it took for Kepler to write his first book with his commentaries on the motion of Mars, his first 2 laws, and then it took him another decade of hard work to discover his 3rd law. This was really very hard work, but Kepler discovered the way the planets move around the sun. Kepler's first law: each planet moves about the sun on an orbit which is an ellipse with the sun at one focus. And so here I've drawn an ellipse, and the sun is at one focus of the ellipse. Here's the other focus. It's an oblong. They're equally spaced about the center of the ellipse. And the planet moves about on the ellipse. The description of the curve is actually the distance from the sun to the planet and then to the other focus. The sum of that distance is constant all the way around the orbit. The long axis we call the major axis, and half of that we call the semi-major axis, and that's the thing that we define with the letter A, and for the Earth, that is the astronomical unit. And so when you were taught, when you were 4 years old by your mother, that the distance to the sun is 150 million kilometers, what she meant to say to you was the semi-major axis of the best elliptical orbit describing the Earth's motion about the sun has a distance of 150 million kilometers. Kepler discovered in his second law that as the planets move around the sun, they speed up when they get closer to the sun, and they slow down when they get further. Now, the Earth is closest to the sun around the 4th of January. That's perihelion, and it's the farthest from the sun 6 months later. So now we're at aphelion, our farthest distance from the sun. And so our distance from the sun varies from about 147 million to 152 million kilometers. There's not just a single number that answers the question, how far away is the Earth from the sun? And so what we're looking for is that number, the semi-major axis of the ellipse that best describes the Earth's orbit. This, by the way, the reason the planet speeds up and slows down is because of gravity. And this diagram is really, in modern terms, it's conservation of angular momentum. And even our first-year undergraduates can derive this and understand it well mathematically. Now, 10 years it took for Kepler to discover his third law. For 10 years, he tried to fit the orbits of the planets into a harmonic series based on the music of the spheres from Pythagoras from 2,000 years before. And when that didn't work, he finally gave up his cherished idea of the music of the spheres. And these are actually from his book here. And he found his third law, and there it is. The period of the planet around the sun, measured in years, squared times itself, is equal to the semi-major axis of its orbit, measured in astronomical units, times itself twice. 10 years for that little tiny equation. And yet that equation is fundamental to much we do in the universe. And for those of you who were with me 6 months ago when I talked about mass in the universe, it's Newton's form of that equation that lets us determine the masses of everything in the universe. Isaac Newton came after Kepler, next generation. And in his youth, he had to leave Cambridge. He had to go back home and get out in the country because of the plague. And in his early 20s, he invented his 3 laws of motion. The first one being inertia, an object in motion will continue in motion unless acted upon by a force. His second law is force equals mass times acceleration. And his third law, you know well, for every action, there's an equal and opposite reaction. That's, of course, what drives rocketry, launching things into space. In order to work on his laws of motion, and he invented the law of gravity, and to find out how the planets move around the sun, he needed calculus, and it didn't exist, so he invented it. And so in his early 20s, he invented calculus, he invented Newton's laws of motion, which we still use for most of our physics calculations. He invented his law of gravity, and from that, he derived Kepler's laws of motions of the planets, and he knew he was right because Kepler had actually used observations and found those laws by measuring the motion of the planets. Newton had a slightly different form of Kepler's third law. The period squared, the semi-major axis cubed is still there. This is just a number, but it also depends on the mass, in this case of the sun, and the mass of the planet. And Kepler didn't know that because the planets are so tiny compared to the sun. That was an important improvement that gives us masses in the universe. Now, taking you back a generation before Newton, in 1618, in Toxteth, just outside of Liverpool at the time, but now within the boundaries of metropolitan Liverpool, Jeremiah Horrocks was born. His family was reasonably well off. His father, his grandfather were watchmakers. They were technical. They had some reasonable income. And Horrocks, there was sufficient income that Horrocks could be sent to Cambridge to university in his teens. He did have a position as a sizer, which meant that he had jobs cleaning up in the cafeteria, tutoring other boys who had plenty of money. But he was learning then the Cambridge curriculum and also the most recent science. He was learning Kepler's new astronomy. And Jeremiah Horrocks mastered Keplerian astronomy in his early teens better than anybody else in the world. He was the world expert. His observations allowed him to show that the moon moves on an elliptical orbit according to Kepler's laws. And Kepler had predicted that Venus would pass in front of the sun in 1631. That was the year Kepler died. So far as we know, nobody watched that. Kepler miscalculated and didn't realize that this would happen again in 1639, but Horrocks, remember, he's just mid-teens, recalculated Kepler's tables and found that Venus would pass in front of the sun in 1639. And he was then in Muchhool in Lancashire. And on that day, he managed to watch the transit of Venus cross the face of the sun. His friend William Crabtree in Manchester also watched it. So far as we know, they're the only two who saw the transit of Venus in 1639. Horrocks then planned shortly thereafter to go visit Crabtree. They had never met. They were living some tens of kilometers apart. It was a long, expensive trip for them. And for reasons nobody knows, the day before the trip, Horrocks dropped dead. He was 22 years old. We don't know what happened to him. He was almost lost from history, but not quite. Some of his papers were found, and of course he became famous. He became famous in the Victorian times. And so this painting, which shows Horrocks completely anachronistically dressed in some Victorian pilgrim's outfit here, watching a projection of the image of the sun onto a piece of paper as Venus passes in front of the sun. And he was watching there from a window in a house called Carr House, which is in Brotherton, in Muchhool in Lancashire, about 20 kilometers away from Preston, where I have an appointment also at the University of Central Lancashire. And during the 2004 transit of Venus, I was one of the main organizers of an International Astronomical Union meeting on fundamental astronomy, including transits of Venus that we held in Preston. And during the transit, we went down to Carr House. The owners very kindly hosted us, the BBC, Patrick Moore, schools, and we actually watched the transit last 6 hours. We watched parts of it from the window that Jeremiah Horrocks probably watched the 1639 transit. So transit of Venus happened 1631 and 39. Kepler predicted 31. Horrocks predicted 39. After that, it was well known when they would come. They come at a little over a century, and they're two of them 8 years apart. That has to do with the relative orbital times and positions of Venus and the Earth. So they knew that there were two more transits coming in 1761 and 1769. Horrocks was aware that this might be used to get the distance to the sun. He very crudely tried to do that, and he got about 60% of the astronomical unit. But that was a great improvement over anything that had ever come over the thousands of years before him. Then the Royal Society was founded in London in 1660. This was following the Civil War. King Charles II was put back on the throne and was the patron of the Royal Society. This was a society initially of men who were meeting to discuss science and natural philosophy. Isaac Newton was one of the founders. Another one of the founders, I've shown you a picture here of St. Paul's Cathedral, because another one of the founders of the Royal Society was the civilian professor of astronomy at Oxford until he was 29. And then he decided not to be an astronomer anymore, and he changed careers. He became an architect. And he was the architect of St. Paul's, 50 other churches. And if you go to St. Paul's, you go down into the crypt, you can find the tomb and the plaque to Christopher Wren, which his son put there. And on it, it reads, "Reader, if you seek a monument, look around you," meaning St. Paul's Cathedral. So the Royal Society was founded in London for the advancement of science. Well, the French aren't to be outdone. 1761, King Louis was deeply in debt in France. He had a completely kleptocratic minister of finance who he got rid of and replaced him with the great Jean-Baptiste Colbert, who became his minister of finance for more than the next 2 decades, got the French finances back in shape, the taxes back in shape. By 1666, there was a surplus of money, and Colbert began to build. He was one of the people who pushed for the Académie Royale de Sciences, France's Royal Academy. He also was the one who agreed to fund l'Observatoire Royal in Paris, starting building in 1667. For those of you who've been to Paris, if you haven't been to this, it's on the Arago line. Francois Arago was a French astronomer, and the Arago line was the line that the French wanted to be the line of longitude 0. That argument with England was eventually won by England. It became the Greenwich meridian, but there is still an ergo line of longitude that runs through the observatory and down to the Jardin de Luxembourg, where, if you know Paris, you very probably have been. It's where the French Senate meets, and beautiful gardens. This is the observatory where Foucault first hung his pendulum to show that the Earth rotates. And Colbert started staffing this with lots of money, basically the way a modern football team buys football players, paying big salaries, offering big perks, nice offices, good French food, good working conditions. They tried to coax Newton into coming. He refused, but they did a good job of building a big observatory and hiring top people from across Europe with great salaries, great enticements. Well, England's not to be outdone. France has a Royal Observatory. Then in the next decade, the Royal Greenwich Observatory is built in Greenwich. It's built with used brick from demolished buildings that were already near the site. It was paid for with the sale of spent gunpowder from the Royal Navy. The wood for the trusses for the roof and for the doors came from an old disused door out of the Tower of London. And it had one astronomer royal and one assistant. And so it was done on the cheap. And the great competition between the French and the English with their two academies and their two observatories in the early 1700s was the determination of longitude at sea. The astronomers wanted to do that using the moons of Jupiter, the phases of the moon here at the Earth, but John Harrison invented a clock that could keep time at sea. A pendulum clock obviously can't, because the pendulum will swing with the motion of the ship. And many of you will know this story from Dava Sobel's very nice history of that, called longitude. So Harrison solved that problem. That problem was done. And the next thing that the academies and the observatories set their attention to, and then all of Europe in competition, was to find the distance to the sun. Edmund Halley, Astronomer Royal, civilian professor of geometry, Royal Society secretary, he advocated in 1616 that when the transit of Venus came in 1761 and then 1769, the opportunity better not be missed. If it's watched from different places in the world, triangulation will give the distance to the sun. Halley's recommendations were accepted, and expeditions went out from Europe, 100 astronomers. This competition was expensive at the level of modern terms. This is a scientific competition, and the cost is similar to the James Webb Space Telescope. This was major, big science for the very first time, with 100 astronomers, many, many expeditions, traveling around the world in order to get in different positions to triangulate the distance to Venus in order to get the distance to the sun. And so here, actually, from 2004, is a time-lapse movie from a telescope, the Canary Islands. You can see in the bottom how fast time's running, of Venus silhouetted against the sun and moving across the face of the sun. The meeting that I ran, we were at Majul, we were watching this. We watched this through our telescopes, and just with, even with just a solar filter, like for an eclipse, we could see Venus passing across the sun with our naked eyes. And so it's to time how long it takes Venus to go across the sun. Here's the technique. Two observers in a different place on the Earth, well surveyed so they know exactly how far apart they are, watch Venus pass across the sun. They see it pass across different chords, and by timing how long it takes, they can figure out what the latitude is on the sun, and that then measures this angle right here. Well, these are two crossing lines. That angle is equal to this angle over here. You know the base of the triangle by surveying, and you can solve this isosceles triangle and measure very precisely the distance to Venus. And of course, Copernicus had already shown us that the distance from Venus was 72% of an astronomical unit. That gave the distance to the sun. 1761, the Royal Society with the Royal Navy sent out a ship called the Seahorse out of Southampton, and the astronomer leading the trip was Charles. He was the assistant astronomer at the Royal Greenwich Observatory. He was paid a mere £24 a year and could survive on that, but not well. He couldn't find another astronomer to go with him as an assistant, but he found a surveyor, which is necessary too, named Jeremiah from County Durham. And Charles and Jeremiah sailed in December 1760 out of Southampton on HMS Seahorse. They had not been gone long before they sailed into the way of a French ship called Le Grand. This was during the 7 Years' War. And in the battle that ensued, Le Grand basically blew the Seahorse out of the water. It limped back to Southampton with 11 dead and 37 wounded. This was tough being an astronomer back then. Charles and Jeremiah were horrified and sent a message to London, to the Royal Society, that they would not get back on that ship no matter what. They're not going back out again. We will not proceed thither. Let the consequence be what it will. The Royal Society responded quickly and said their refusal to proceed after having so publicly and notoriously engaged in it would be a reproach to the nation in general, to the Royal Society in particular, and more especially and fatally to themselves. It could not fail to bring an indelible scandal upon their character and probably end in their utter ruin. The Society noted that it would, with the most inflexible resentment, prosecute them with the utmost severity of the law. Charles and Jeremiah saw things differently at that point. They got back on the ship once it had been repaired, and in February of 1761, they sailed out of Southampton again. They were to go to Bencoolen in Sumatra, on the other side of the world, and so they needed many months to get there. There's the Seahorse. It sailed into Table Bay in Cape Town in South Africa. And there in Cape Town, this is of course modern Cape Town, not as it looked then. There in Cape Town, they heard the news the French had taken Bencoolen in Sumatra. They couldn't continue. And they were actually pleased. And they watched the transit of Venus from the parade in what is now downtown Cape Town under the view of Table Mountain. They measured their position to very high precision. And it was a clear day and they were completely successful. Their observations were very useful. It was a successful transit of Venus observation. They became famous in the British Empire as the most important surveyors in the entire empire. Well, in the colonies in North America at that time, two of the colonies, the Pennsylvania with the Penn family running it, Maryland with Lord Baltimore and family running it, they had a dispute in the courts that was settled in 1763. And with the lawyers finally agreeing, they wanted to survey the boundary between the two colonies. It was a line running straight east to west, out through the wilderness. And for that, they wanted the most prominent surveyors in the British Empire, Charles and Jeremiah. And so Charles and Jeremiah sailed to North America, and they spent 4 years measuring the boundary between those two states. And when it was done, it was named after them. They were Charles Mason and Jeremiah Dixon. The line's called the Mason-Dixon line. It divided the North from the South, free states from slave states. And it's argued, and is quite possibly true, that the entire South, Dixie, is named after Jeremiah Dixon. And so the next time you happen to like listening to Dixieland jazz, you might think that there's a connection there to the transits of Venus and the attempt to find the distance to the sun. Well, the observations weren't good enough. And so the expeditions went out again in 1769. And at that time, the Royal Navy decided to send the expedition out in a refitted colliery ship. It used to haul coal. Here it is sitting in Whitby Harbor in Yorkshire. And it's to go to the other side of the world, to the newly discovered, for Europeans, Tahitian Islands. No Royal Navy captain would take command of the ship. They felt there was no career prospect in taking some astronomers out to watch some Venus pass in front of the sun. So they persuaded a young officer who had been making a name for himself surveying in Canada to take the command of the ship. He was promoted to captain, and they sailed out on the way to Tahiti on the greatest sailing expedition of all time. The captain's name was James Cook, and the ship was the Endeavour. They did successfully observe the transit from Point Venus, just north of Papeete in Tahiti, and their observations were useful. But of course, Cook's exploration on to Australia, New Zealand, down south to show there was no great southern continent, made it the greatest sailing expedition there ever was. That was a career-making move that all those other Royal Navy captains missed out on. Now, I just want to tell you one more story, and I'll finish up with where all this is going. A Frenchman went out to Ile-de-France, or Mauritius as we know it now. His name, Guillaume Joseph Hyacinthe Jean-Baptiste Le Gentil de la Glacière. We call him Le Gentil. This is a painting of a French nobleman, if you like. And he went out to Mauritius to observe the transit. He decided the best place to observe it from would be the Philippines. He sailed to the Philippines, but the Spanish governor there took him to be a spy, and Spain was supporting France in the 7 Years' War, and Le Gentil was imprisoned. Finally, because he was a scientist and through a lot of letters, managed to get out of prison, sailed away to go to India to watch the transit, and he got caught out at sea. It was a beautiful day. He watched the entire transit, but he couldn't survey where he was, and his observations were useless. Because of the war, he was afraid to go back to Europe, so he went back to Ile-de-France, and he spent the next 8 years surveying in the Indian Ocean. And then come the 1769 transit, he went up to Pondicherry, where he was welcomed by the ruler. He built an observatory. He was well treated. The night before the transit, everything was perfect. The weather was great, but during the night, the wind came up, the rain came, and throughout the transit, howling wind, pouring rain. And the storms finally cleared and the sun came out just as the transit was over, and Le Gentil got nothing. He went back to Mauritius to pack up to go home. And as he was doing that, an English warship sailed into the harbor and scuttled his ship. He then had to hitch a ride later on a Spanish ship around, reprovisioned in Cape Town, and then coming up the coast of Africa, they were taken by an English warship. And the Spanish captain said to the English captain that, no, you can't do this. The war's over. And the English captain says, yeah, right, tell me another one. But the Spanish captain said, no, we've picked up newspapers in Cape Town. And indeed they had. The war was over. And so the Spanish gave the English some sherry, and the English gave the Spanish some potatoes. They had a nice little party together. The ships parted. And eventually Le Gentil's ship put him off in Portugal, and he walked back to Paris, where he discovered people were absolutely astounded because he had been declared dead. All of his possessions, his estate, were given to his heirs. He had lost his seat in the academy, given to another person. And so with the help of some lawyers and the rest of his life, he recovered quite a bit of his belongings and his estate so that he could live reasonably well. He was given a special seat on the academy, and he lived more than 2 more decades, but he chose never to do astronomy again. There is his book that he wrote about his adventures, Voyage on the Indian Ocean by order of the king, on the occasion of the passage of Venus over the disk of the sun on the 6th of June, 1761, and 3rd of the same month, 1769. There are the diagrams, but his observations weren't useful. Finally, all of the expeditions were put together by Jérôme Lalande, who calculated from the transits the distance of the astronomical unit, 153 million kilometers, plus or minus 2 million. It's very good. The modern value, 149,597,870,700 meters. And I would like you to memorize that. None of this 150 million kilometers anymore. Somebody asks you the distance from the Earth to the sun, there's the number you should be giving them. What that told us, we knew the distance to the sun. What do we get from that? All of a sudden, we knew how bright the sun was. There's the first payoff. 384 septillion watts. Oh, what powers the sun and what powers the stars was one of the first results of knowing the distance to the sun. Of course, it also then raised the possibility, it's the fundamental way that we find out how far away everything else in the universe is. So when somebody asks you how far away is the sun, again, instead of just say, oh, it's 150 million kilometers, you can now tell them what you really know, 149,597,870,700 meters. We know that distance to just a few meters. The Earth doesn't move completely in an ellipse. The moon tugs it around, the other planets tug it around, and it wiggles a lot. And so even the ellipse is an approximation. Now, I've gone on very long, folks. I can see that. I need to leave time for some questions. Thanks for your patience for this. I enjoy telling this story. Let me stop with that, and we'll move to question time. Andrei, I'm not hearing you.
Thank you very much, Don, for this absolutely fascinating talk and such a rich history of discovering that number, which of course we all memorized. And now there is time for questions. And let me just ask question I had. You mentioned that Greeks have been quite erroneous in their estimate. Can you just illuminate a little bit? How did they try to measure it?
Andrei, up until the transits of Venus, the method for trying to measure the distance to the sun was to measure the parallax of the sun. From two different points on the Earth, the sun would be in a slightly different direction, but it's blindingly bright in the sky, and the difference is a tiny, tiny angle, and the edge of the sun's not easy to determine. And so over a couple thousand years, the distance to the sun was attempted to be determined by parallax of the sun, slight shift if observed from different places on the Earth. And that gave some indication that it was farther away than the moon. The Greeks had, I think Aristarchus had it 20 times farther than the moon. So it was in the right direction. But of course, if it was only 20 times farther than the moon, then it's only 20 times bigger. And that was the only method, was the solar parallax, until the transits of Venus. Now, the way we measure the distances, we've got satellites orbiting the sun, we've got radio communication with them, we can put in general relativity and the tugs of all the other planets, and it gives us these distances to meter precision. Stunningly precise.
Stunning, yes, indeed. Thank you. There is a question from Martin Cook. Was there religious concern about the astronomical pronouncements?
Oh, Martin, I'm not sure exactly what time you're talking about, because we're looking at over many, many years. But yes, there were always religious concerns about astronomical pronouncements. You probably know the story of Galileo, where Galileo wanted to believe in Copernicus, that the sun was at the center of the solar system, the Earth moved, and he was forced by the Inquisition to recant that. There's a possible myth, possible truth that he mumbled after he recanted, but still it moves. That's not certain, but he was a friend of the Pope. He was well respected, and they weren't going to burn him at the stake, but he was held under house arrest for a long time. There was a case. Of course, Copernicus himself was a canon in the church. And so times were changing then, and it was discovered that the skies weren't unchanging, and religion was going to have to accommodate and give way to the scientific results.
Thank you. Thank you. People are still quite fascinated by such a precise number up to the meter. So maybe you could a little bit clarify. Mick Rawlings asking, really interesting. Only one thing, could I think, was the distance being defined, but traveling in ellipse must vary slightly?
That distance for the astronomical unit was defined by the International Astronomical Union to be precisely that number I just gave you in 2012. Prior to that, the digits went right down to that last digit in meters, and the precision was about 3 meters. But when I ran that meeting for the transit of Venus in 2004, one of the people I invited to the meeting who came was a man named Miles Standish, who is the keeper of the solar system at Caltech. His model is the international model. There's one other, but the international model for the Earth's motion about the sun are entire observations of solar system bodies. And I said to Miles during the meeting, and in fact, I recorded the conversation, it's in the Transit of Venus proceedings that are published after that. I said, would you please define precisely what you mean by the astronomical unit? Because it's not an ellipse, because the Earth wiggles and is not in an elliptical orbit perfectly. And in fact, because of the tugs of all the other planets, once the Earth goes around the sun, it doesn't end up back where it started. It's not even a closed curve. Said, will you please finally, because all of us need to tell our students this and answer questioners when we're giving talks, what is the answer to this? And he said, I'm not going there. It's what's in my model. So I'm stuck giving you a better answer. That number that I gave you is the number that's put in the model of the solar system that fits the orbits of all the planets, the asteroids, and everything else in the solar system. But just realize that it is not the semi-major axis of an ellipse that fits the Earth's orbit, because the Earth's orbit at that position is not perfectly elliptical. And you need general relativity to do this too. This is not just Newtonian physics. The general relativity affects the Earth's orbit. So you've asked a very complex, hard question, and the best I can do is pass on the answer I got from the world expert on it, who said, I'm not going to answer that, it's in my model.
There are two connecting somewhat questions. One from Steve Deveau. Were transit of Mercury considered as a method of calculating the astronomical unit? And the second, another question from Timur, who asked, do we know how close was the first approximation of the distance got with the transit of Venus? Could other planets be used? And if yes, how effective the method would be?
Okay, Stephen and Timur, those questions were partly coupled. And I don't know if the transit of Venus was ever used for a very precise measurement of the distance to the sun, because the transits of Mercury, because the transits of Venus were observed first. And why Mercury being in a smaller orbit, it makes it harder. Mercury does transit 13 times a year. And so that's an advantage. But I personally don't know of transits of Venus being used for distance, but it's possible that they have been. So I'm not saying that it hasn't. I just don't know the answer to that. And now there was a second part to Timur's question, Andrei.
It was what was the kind of first approximation of distance?
Oh, yes, for the 1760. I don't know the answer to that, Timur, but somebody else does. I don't remember the number that was got from that first measurement. One of the problems with the measurement is that when Venus is just on the limb of the sun, something called the black drop effect occurs. And there are a variety of explanations for why that is, but it doesn't just sharply cut off. The sun's atmosphere is not sharp. There are optical effects, and the timing across the face of the sun is difficult, and that leads to errors. And the realization of that in 1761 led to improvements in 1769. So I don't know the answer to your question. Probably somebody else does. I'm sure the calculation was made, but I don't remember the answer to that.
Okay, thank you. There is a question from Daniel Wainwright. I inferred from something you said a few minutes back that we now estimate the distance to the other stars by their brightness relative to the sun. Is it what you mean?
No, Daniel, was it?
Yes.
Yeah, Daniel, no, I'm sorry if I implied that. We measure the distances to the stars by parallax, but that's the parallax of the Earth's orbit. So from the Earth orbiting from one side of the sun to the other, we can measure the shift of the position of the stars in the sky and triangulate to them, just like a surveyor triangulates. And knowing the astronomical unit gives us the baseline, and we can measure the angles. We now do that with a satellite called Gaia, and it is measuring the angles to a precision of a few millionths of an arc second. Incredibly precise, and that allows us to measure directly by triangulation distances to stars almost out to the distance to the center of the galaxy. From there, we have to use other techniques, and ultimately, when you go to galactic astronomy and you're looking at expansion of the universe, for some purposes there, the distances to the galaxies are estimated by their brightnesses, as in the question you just asked me for the stars. But we don't do that for the stars. We can do much more precise measurements for them.
Thank you. Now question from AC, believe San Diego. Why couldn't the astronomical unit be defined at the distance of on a particular date, such as on the date of the Venus transit, where the measurements provided the answer to the distance?
AC, let me actually reverse your question in my answer. We need to characterize the Earth's orbit with just one number. And the varying distance is not a good way to do that. So the semi-major axis, to the extent that the orbit is an ellipse, and that's a good approximation, that semi-major axis is just one number that characterizes the orbit. On the day of the transit, the Earth would not have been one astronomical unit away from the sun. What was measured was the distance from the Earth on that day to Venus on that day. And that then had to be calculated with the distance the Earth was actually from the sun, and from that calculate the astronomical unit, which was a different number. That was the semi-major axis of the orbit. And so your question was, yes, what you asked about had to be taken into account, but the number that we characterize it by is just a single number, so we don't have to have lots of different numbers for the distance on different days.
Thank you. And now the question, people probably very fascinated by this 700 meters precision. Jerry Brown is asking, when we talk about distance to the sun, is that to the center of the sun? Because sun doesn't have a solid surface to measure.
Okay, this is Jerry, is it?
Yes.
Yeah, Jerry, the question, like almost always, the questions are more complicated than what I've previously told you. No, it is not to the center of the sun, because the Earth, let's take the Earth to be in an elliptical orbit. Let's leave out the perturbations from the planets. That ellipse, it's not the sun that's at the center of the ellipse. It's a point in the solar system called the barycenter, B-A-R-Y center, and that's the balance point between all the masses in the solar system. Because the planets don't just orbit the sun also orbits the planet. Newton's third law. Every action, there's an equal and opposite reaction. Take Jupiter. Jupiter has 1,000th the mass of the sun, so the point that Jupiter and the sun orbit is 1/1000th the distance between them. That's outside the surface of the sun. And so this astronomical unit that I'm giving you, and the precision isn't, the 700 meters has been rounded to give it, it's been made exact by the International Astronomical Union. It's known to better precision than that. That is to the barycenter of the solar system, which is the balance point amongst all the masses in the solar system, and that's moving about all the time. And we do very precise calculations in all of our observations to keep track of that. When I observe variable stars and I give the times for my observations, I correct those times to the barycenter of the solar system so that the Earth's motion doesn't actually change the timing as the Earth gets closer and farther from the star I'm observing. So we take great care, and the barycenter can move about by about 2 seconds of light time. If you're observing a pulsar which is rotating 700 times per second, the difference between the center of the sun and the barycenter can be 1,500 rotations for the pulsar. It's a big deal for a lot of observations.
Thank you. There are more interesting questions. Martin Cook is asking, did the calculations of Kepler indicate differing planetary planes of orbits?
Oh, yes. Kepler knew that the planets were not in the same planes. And that was why Kepler was able to predict the transit of Venus of 1631. And it's why there isn't a transit of Venus every time Venus passes between the Earth and the Sun, because Venus and the Earth aren't exactly in the same plane. And it turns out that there's about the period between them is what's called the synodic period, and 5 synodic periods brings them back into the same plane again, and that's 8 years, which is how we get the 2 transits 8 years apart. But then because of the tip of the orbit, all that doesn't come back together again for over a century. And so, yes, Kepler was aware that the planets were not all in the same plane. He knew that.
Thank you. Another question from Marisa Muselli. Will the distance between Earth and the Sun ever change? And if so, why, how?
Okay, the distance between the Earth and the Sun, that semi-major axis of the astronomical unit, is changing all the time by a small amount. And on time scales of hundreds of thousands of years, it's changing significantly. Because the tug of the other planets on the Earth, the gravity of the Moon, causes the Earth's orbit to become more and less eccentric. We currently have an eccentricity. This number measures how far away we are from a perfect circle, which is a little less than 2%. But that number grows and decreases with cycles that are called the Mikhailovich cycles, on timescales of 50,000, 100,000 years, and it seems almost certain that some of the ice ages are coupled with those cycles, because the Earth's orbit not only changes eccentricity, but the tip of the Earth with respect to its axis, the 23-degree tip, is also variable with time. And then the sun is losing mass. The sun has a wind. It's blowing, the wind's very small, but it's blowing away enough of its mass at all times. I mean, that's what's hitting the Earth and producing the aurorae that you're seeing occasionally, maybe even a couple of weeks ago. That mass coming off the sun's reducing the mass of the sun, and with that, the Earth's orbit is growing larger because the sun's mass is growing weaker. And over the lifetime of the sun of 10 billion years, mass loss from the sun will be significant. Late in its life, the sun will blow away 10, 20, 30% of its mass, and the Earth's orbit will expand because of that. And so, sure, the Earth's orbit is changing. On a human time scale, no, but on a long time scale, yes.
Thank you. Now, Neil Ormus is asking, the recent transits of Venus were observed in thousands of places. Did those observations result in a good approximation of the distance that agreed with more sophisticated radar measured values?
Oh, do you know, I don't know if people used the transits of 2004 and 2012 to calculate the astronomical unit. I'd be surprised if somebody didn't do that for fun. Excuse me. The last time that was done scientifically to determine the astronomical unit was for the 1880 transits, and it did end up with an improved astronomical unit. It wouldn't be done scientifically to improve this astronomical unit because the number is known so much better from the satellites orbiting the sun, from radar beams bounced off of other planets, the measurements we can make. But I don't know the answer to your question, but I'd be surprised if somebody didn't do that for fun. And possibly sometime over the coming days, I'll go look to see if I can find it.
Thank you. We're approaching our time, but there is one more question from AC. Over the eons of time, would the solar system approaching another star that astronomical units would change due to gravitational force?
AC, if we pass close enough to another star, or use your science fiction mind on this, what if a black hole comes in and passes close? That could disrupt the solar system. It could change the orbits. And there certainly are stars in the galaxy, particularly in very dense clusters where solar systems may pass close to each other and completely disrupt solar systems, eject stars from the solar systems. Keep in mind the scale of our solar system here. If I shrink the sun down to the size of your head, there you are in San Diego, and I shrink the next nearest star to the size of my head, the distance between us, it's a little bit closer than from you and me in South Africa and you in San Diego, but not a whole lot. If the stars are the size of our heads, it's a long way between the stars out where we are in the galaxy and where the sun is. And as the sun orbits about the center of the galaxy, it very probably hasn't passed close to any other stars to disturb the orbits of the planets, and probably won't in the rest of the lifetime of the sun. But elsewhere in the galaxy where the stellar density is higher, sure, it happens. Star systems can be torn apart. Planets can be disrupted. Yeah, it happens. Not to us, not for something for you to worry about in your lifetime.
Thank you. Thank you very much, Don. We now approached our end time. It was absolutely fascinating. Thank you, everyone who participated in this chat, asking questions. And we wish everyone very good evening, day, wherever you are now. Also good summer or winter months ahead, and we'll try to meet again in the beginning of academic year and talk about some other fascinating astronomical astrophysics topics. Thank you very much, and thank you very much, Don.
Okay, and thank you all for coming. I enjoyed being back. I hope you did too. Bye.
Bye. Bye.